So let us now try to find out the wave equations, or essentially the equation for these vector and scalar potentials, and thereby we should be able to solve it to find out the solutions of the phi and a, which should obviously be in terms of the rho and j, because those are the source things. Source things by so these rho and j are called the sources because these are the sources of the electric and magnetic field, or the sources of the scalar and vector potentials. So let us begin by the equations that are relevant for this. So remember, we have these two interesting equations. One is del dot d is equal to 4 pi rho, and another is, so this was my equation number 1.1, and then we also have the curl of B. In fact, we will discuss the equations in absence of medium. So that is going to be del cross B minus 1 over C del E del T, and that should be equal to 4 pi by C J. Okay, so this was my 1.3. So these are in the absence of media. That is, we are talking about the vacuum. Epsilon is equal to 1 is equal to mu. So now let's take the let's try to put the values of E, and so putting E is equal to minus gradient of psi in these conditions del A del T, and B is equal to del cross A, and if required, of course, we will be using further equations, okay, in the respective equations. So let us take the equation number 1.1. That's going to be del dot E, which is minus del phi minus 1 over C del A del T, and that should be equal to the 4 pi times the charge density. So this will give us del 2 phi, and minus plus, we are sending it on the other side. This is going to be 1 over C del over del T del dot A. This is equal to minus 4 pi rho, and now our gauge condition. So we will use the gauge condition, which is del dot A is equal to minus 1 over C del phi by del T. What we will get? So let's put that value over here. We'll get, I'm sorry, this should be plus because we have taken minus common. So this is going to be minus 1 over C square del 2 by del T2. And that should be equal to minus 4 pi rho. And let me put this as equation 7 because I'm still continuing with the previous lecture. So this is the equation for phi. Similarly, 1.3 gives. Let's see what 1.3 gives. 1.3 will be written at del cross. B is going to be del cross A, and then minus 1 over C del T of minus gradient of phi minus 1 over C del A by del T is equal to 4 pi by C and the charge density. So now let's simplify these things further. So this will give us minus del 2A plus del dot del of del dot A. Okay, so this is going to be this, and then minus 1 over C minus 1 over C minus plus 1 over C del t of gradient of phi. So this is going to be 1 over c gradient of phi, this is going to be 1 over c gradient of del phi by del t, and let us check the sign. So this is going to be a plus sign, and minus minus plus 1 over c square del 2a by del t2. So this is going to be 4 pi by c j. Now let us put the value of del a. So this is going to be 1 over c del phi by del t. And this is what? So that is going to be gradient of del phi by del t, gradient of del phi by del t. So they will cancel, and therefore we will get the Laplacian square a minus 1 over c square del 2a by del t2, and that should be equal to minus 4 pi by c j. So this is equation number 7.2. So what would be the solutions? Well, so these will become Laplace equation if there is no source. So in the absence of sources, that is what we have, rho is 0 is equal to j. What we will have? We will have del 2 minus 1 over c del 2 by del t2. And whether you talk about the phi or you talk about a, you are going to get the same thing. So that's how we write these equations. So the solution should be an obvious thing for them. And also now, so this is the situation. And also if we have the static electric and magnetic field, for static electric or magnetic field, what we will have? We will have del over del t of phi or a, that should be equal to 0, and therefore these equations would be del 2, the Laplacian of phi, that's minus 4 pi rho, and del 2a is equal to minus 4 pi by c j. So these are equations 9. So if we want to write the solution from here onwards, what would be the solution? That's going to be phi r. There wouldn't be time. So this should be the density. So imagine these are the locations we are starting off. So suppose we are talking about a volume over here located at a position r, and suppose this is where we are looking for the field, that's a distance r prime. So then this is going to be r minus r prime. Okay. So when we talk about the volume, we are essentially talking about this one. Okay. So this is going to be, I'm going to write the solutions out here. So this is going to be rho r prime, because this is where the volume is constrained, and then upon the distance, that's how we write potential. Potential is written as q over r. So this is q is rho dv upon r. So that's it. Similarly, and well, it should be dr prime. So this is dv prime. Similarly, I'm sorry, this should be just opposite. So I should write dv, that is going to be fine. So this should be r prime. Okay, or let's just write it this way, and then we will repair this to be r prime. Okay, so similarly, we could write the a, and that would be, well, we could guess, we will have a factor of 1 over c, and then we will have j, should again be r prime, because we are talking at a distance r prime, and this should also be r minus r prime. So these are all the solutions. Now if, for example, using these, suppose somebody asks you to do the value of electric field. So you could write even those values as well. So let me, for the sake of completeness, write the values of the value of E. So therefore, electric field, which is minus gradient of phi minus 1 over C del T. So this is going to be minus gradient of phi. So gradient of phi, that would act over 1 over r, you know it's going to be 1 over r square. So the naive guess would be this is going to be rho upon r square. So this is going to be rho upon r square, and the direction of electric field, because del dot E should be 0 and therefore it should be pointed along the r hat vector. So this is going to be r hat, and then we should write minus 1 del gradient of minus 1 over c del t. So therefore we will have minus 1 over c is here, 1 over c is there, 1 over c square, and del over del t, so that will give you del j by del t. However, we had 1 over r in the previous expression, so that should also stay, and then this whole thing should be, so this was this rho should be integrated over the whole volume to get the charges and the current. So this is how we should be able to obtain the solution. So remember what we had done. We had started with the Maxwell's equations, and from there we had guessed the forms of the vector and the scalar potentials. Then we had done the gauge fixing and the gauge transformation. So using the gauge transformation, we have been able to write down the wave equations for phi and A, which for the electrostatic case had been solved in terms of rho and j, and then ultimately using the form of E, we had obtained a solution for the electric field, which looks like this integration. So this is how we should be able to work with these things, and that's how we will be able to, we will be learning more and more interesting things about the systems where both these waves are present. Thanks.